Every species on Earth carries a built-in clock, hidden deep in its DNA. They don't change the letters of our genetic code, they decide which genes get expressed, like light switches that get turned on or off. This is known as epigenetics. Over the years, these tiny molecular marks shift in recognizable patterns. Dr. Steve Horvath discovered that we can study these patterns within methyl groups to measure biological age, creating a powerful biomarker known as Horvath's clock.
We went through a 7-year effort, 200 people, many millions of dollars spent to answer the question, does methylation explain or correlate with maximum lifespan? And the answer is a definitive yes. There's actually a very strong signal. I'm quite excited about it because it would say that these epigenetic changes do play a role in the maximum lifespan. The question is how and why. Methylation is known as an epigenetic modification of the DNA. More precisely, it's simply a chemical modification. Your DNA contains 4 bases, letters A, C, T, G, and letter C sometimes changes. There's a chemical reaction called methylation. As we age, certain parts of the DNA gain methylation, other parts lose methylation. That's well known. But what we have shown is that the speed by which you gain methylation at certain locations, that relates inversely to the maximum lifespan of the species.
By studying methylation patterns in different species, scientists gain a better understanding of methylation in humans. They learned it isn't just where these chemical tags appear, it's how fast they change. This tempo, this rhythm of molecular change, is known as methylation dynamics.
What we can already tell is that long-lived species have a methylation landscape surrounding their DNA that is, in certain ways, an interesting landscape. There are peaks, high methylation, there are valleys, low methylation. By contrast, short-lived species, they have a more boring, flat landscape. The key insight is that long-lived species accumulate methylation changes more slowly. Imagine you have a valley on the DNA where you want to have low methylation. Then a long-lived species will keep it protected from gain of methylation. So a long-lived species will have low methylation throughout most of the life. By contrast, a short-lived species, like a mouse, will gain methylation quite quickly. It's quite interesting to have that insight, but it also points the way that maybe to enhance the maximum lifespan of a species, you really need to change epigenetics.
Horvath's clock changed everything. It proved that aging could be quantified, that time leaves a signature on our DNA. And that discovery sparked a global movement. Today, scientists like David Sinclair are building on that foundation, using Yamanaka's 4 reprogramming factors to reset the epigenome itself, turning back the cellular clock, restoring function, and even reversing blindness in mice. The practical applications are only beginning to emerge: drugs that slow aging, therapies that rejuvenate tissues, and daily choices that influence how our genes are expressed. For the first time in the history of our species, we are not just studying longevity, we are engineering it.